Hello, discrete math fans. We're going to talk about moving around in graphs. That's accomplished by moving from one vertex to another along a sequence of adjacent edges. Let's take a look at this graph. Okay, we got a graph. We have 8 vertices, 14 edges. We've even got a loop in the graph. Got a couple of parallel edges. Might be useful for you to write down this graph. Now we could walk from V1 to V4 directly by following this route. So when we talk about a walk in a graph, we need to alternate a sequence of vertices and edges. You start on a vertex, you follow an edge, you get to a new vertex. Then from that vertex, you follow a new edge to get to yet another vertex. There's also a very roundabout route that still starts at V1 and ends at V4. You should double check to make sure that this route really does work. Now, certain types of sequences of adjacent vertices and edges are of special importance in graph theory. As an example, those that do not have a repeated edge, that was the requirement in the bridges of Königsberg problem, and those that do not have a repeated vertex. And we'll see this in the traveling salesman problem. And of course, there are others that start and end at the same vertex, and possibly some combination of these. All right, I'd like to define a bunch of graph theory terms. Now, we'll use these a lot, but I don't feel a need to memorize these terms. So you might want to make a list, refer back to it as needed. Okay, so what we're going to define is a walk. This is the most important definition. It's just the basic way of moving through a graph. A walk is simply exactly what we've talked about before. It's an alternating sequence of vertices and edges. This is your starting vertex. This is your ending vertex. So you're going to start at V0, end at Vn. And you can even have a trivial walk. That's the kind of walk where you don't get any exercise. You never leave the house. There's a trail. A trail does not contain any repeated edges. Now that's what we wanted in the bridges of Königsberg problem. We have a path. A path does not contain any repeated vertices. A closed walk is a walk that starts and ends at the same vertex. That's the kind of walk I take when I walk my dogs. I start at my house, I walk around the neighborhood, and then I end at the same place, back at my house. A circuit is a closed walk that contains at least one edge, so you're going somewhere, and does not contain a repeated edge. I try to do this when I walk my dogs, but I'm not always successful. Sometimes I double back on the way I came. A simple circuit is a circuit that does not have any other repeated vertices except the start and the end. Now, of course, when you have a circuit, you have to start and stop at the same vertex, so you're going to repeat that one. But in a simple circuit, there are no other repeated vertices. Now go back to the graph that I presented at the beginning of this video, and let's look at some sequences of vertices and edges. We'll try to determine which are trails, paths, circuits, or simple circuits. And they can be some combination of these. Okay, so remember that this was the graph that I presented at the beginning, so we're going to use this one. You may want to draw a picture of this for reference as we go through this. Okay, here are the 3 walks that I'm presenting. I would like you to try to determine what properties these walks have. Are they paths, circuits, and so on? You may want to pause the video while you work out for yourself the answers. Okay, the walk in A is a trail, and that's because it does not contain a repeated edge. It's also a path because it does not contain a repeated vertex. However, it's not a closed walk because it doesn't end at the same vertex that it started on. The walk in B, it's not a trail or a path because it has both repeated edges and repeated vertices. It is a closed walk because it starts and ends at the same vertex. However, it's not a circuit because it has a repeated edge. And finally, the walk in C is a circuit. It's a closed walk, but it doesn't have any repeated edges. And finally, I'd like to make a definition about connectedness. So let's let G be a graph. We're going to say that two vertices, V and W of G, are connected, provided that there's a walk from V to W. Then we can say that the whole graph is connected, provided that there is a walk between any two vertices, V and W, in G. So the first part, we're defining connectedness between two particular vertices, and then we're saying that a graph can be connected if any pair of vertices is connected. Okay, that's all for now.